And then also your suggestions from your research mentor might provide some other ideas for research for an activity. For instance, you may be working on a certain area of nanotechnology, applied nano, but perhaps your faculty mentor has some ideas on areas that would be useful to fill in students at the high school or even middle school level before they arrive to do these kinds of research projects. So I encourage you to raise the subject with your mentor, see what he or she has to say about potential research or activity or lesson topics. What has been done before has been captured, and you can find a number of places where lessons are found. I'm sure you're familiar with some of these sources. Past RET lessons developed under the previous form of our network, which went by the acronym NNIN, have been captured and are available at the NNCAI website. That link will be given at the end of the presentation. The website NanoHub is a huge archive of nanotechnology, nanoscience, material science related demonstrations, simulations, and curricular materials. So I encourage you to check that out if you haven't already done so. I personally worked a great deal on the NSF-funded NanoLink project, which developed a number of modules, which were really quite simple and direct, simple lessons that could be incorporated in a lot of different subject matter, different STEM subjects. So, and of course, if you've got your own favorite curriculum sources that you've gone to, if you look over what's already existing, perhaps you can think of ways to apply them more to the nanoscale and more to nanotechnology. In other words, nanoizing some of these versions of existing STEM lessons. So these are just a handful of sources that, and there are many more, but these are all things to start with as you're casting about looking for ideas for your lesson. So using your summer research project experience as the basis for your lesson, the first question is, can you use it? There are some concepts that you may be working with that are very abstract, very high level, and you'll need to ask yourself, are these concepts translatable to your grade level? If you think that's a little bit beyond what your students are prepared for, can you get these things off in a qualitative fashion or an indirect fashion? Another question you'll need to ask yourself would be that, do these concepts you're working with in your summer project, do they support your existing class that you're teaching at the existing level? Do they support your learning objectives in physics or chemistry or biology or other disciplines that you're teaching in? So I would encourage you to kind of examine that to see if this research is translatable to your lesson. In addition, a good question to ask is this research broadly applicable? Is it something that you can easily engage students in because it's very tangible or very, it's applied to products they're familiar with? Or is it arcane and very abstract or very specialized? That also, I think, goes into the decision of how can I use the research to make a lesson? Another thing you'll need to ask is, does the research I'm doing require multi-million-dollar pieces of equipment? And you can't do it without that. I mean, some of you will be working in laboratories with high-tech analytical equipment, high-tech deposition or fabrication tools. That's going to be a challenge to directly translate to the classroom unless you can think about or find or build a simpler analog to the device you're working with. And as an example, I'm going to throw out something we've developed here at the Nano Center over the past few years. It's about lithography, photolithography. Many of you are going to be working in a clean room. You're going to be using the tools of lithography to deposit thin films, photo pattern those films, and then etch them to create microscale or nanoscale structures. And as you're no doubt aware, these things require very large, expensive tools in a specialized facility like a clean room. So thinking about translating that type of technology to a classroom setting got us thinking about how could we fabricate or make models, not computer models, but actually hands-on, three-dimensional, tangible models that you can manipulate to do all these steps. The result is our photolithography class, and I'm happy to share with you the information on that class. On the left-hand image there, that's a spin coater. Instead of the $20,000 system to spin photoresist onto a silicon wafer, that spin coater is made out of a computer case cooling fan and a piece of Tupperware, well, Rubbermaid, I guess. And with a little fabrication, you can do that. You can spin on the photoresist very effectively, almost as uniformly as you can in the clean room. And then on the right-hand side, that desk lamp and those masks, that's our version of a contact aligner, which you may be using in your research this summer. Contact aligner simply holds a photo mask over a prepared wafer, shines light through it, and makes an image. And then you develop the image. All that's doable with desktop equipment that we've developed plans for and parts lists for and so forth. So this is one example of, if you want to explore some aspect of nanofabrication, it's possible to build up inexpensive, simple to use analogs of these pieces of equipment. And in some cases, these have already been developed. So that's also a resource for you. I probably don't need to tell teachers what makes a good lesson. You know what works in your classroom. You know what it engages students and what turns them off. So I would encourage you to review the lesson design talk. I thought it was a great talk by Steve earlier last week. And then trust your gut is to say how well you can take a very abstract topic and make it more real and more accessible to more students. And of course, the final analysis is, is it educational, but is it cool? Is it something that's going to leave an impression? Is it going to spark up some interest in nanoscience? So these are all, some aspects of what makes a good lesson. So I encourage you to think about that on the basis of your own experience. So now I'd like to shift to reviewing some of the RET lessons that have been developed. And I had accessible mostly information from the Minnesota project. So you'll see a number of projects developed at the Minnesota site in the early 20-teens, 2012 to 2014. And they kind of spanned a range. You could classify them into groups of being fairly closely related to the summer project that the teacher was working on, and into a group that really was a project that was inspired, or a lesson that was inspired by the summer research, but really addressed a little bit different field or a different application of the technology they were working with. And then there were those types of programs that were inspired really just by personal interest and the teaching goals of the classes that the teachers were tasked to teach. They were not directly related to summer research. And maybe I'm going out on a limb here, but I'm saying all those are fine. You don't have to peg your lesson to your research necessarily, especially if you are strongly interested in an area that you would like to explore further with your classes. So first example here is an activity called Coffee Break with Nano. It was closely related to what the RET was working on. Her research was with thin film coatings that were made of nanoparticles suspended in a liquid typically. There's lots of applications for these in a wide number of fields. But making films this way is subject to some defects that this RET teacher found interesting and translatable to the classroom. So a little bit of background here: when you are working with suspension of fine particles and you dry them out on a surface, if you don't really play with the chemistry, you'll get something like this cracking image here. And then the other phenomenon that is issue, it arises in a number of different applications like inkjet printing and making solar cells out of nanoparticles, is the coffee ring effect. And this is probably something you've seen on your kitchen counter. If you spill a droplet of coffee, there's an evaporation of liquid around the edges. And so there's a bulk movement of liquid which drags particles along with the liquid to the evaporating edge. As a result, you don't get a uniform layer of nanoparticles on this film you've made. They build up around the edges where the evaporation is fastest. And as a result, you don't get even coating. This is a problem and it's being studied in kind of fundamental chemistry terms. But the teacher then created an activity where students would create thin films made from nanoparticle dispersions. They also had the option of making the thin film, or making the nanoparticles, but they could also just buy them commercially. And then students were able to explore several properties of nanoparticles and this whole phenomenon of film cracking and coffee rings. So relatively simple equipment, and relatively easy to grasp phenomena, I think translated into a very good activity, and it was directly attributable to the teacher's research. Another example where the RET developed an activity directly related to the research was this toxicology study on the effects of nanoparticles on a subject organism. In this case, it was brine shrimp. This was kind of an exception in that the faculty member here at Minnesota set out to do this sort of project and was interested in coming up with a publication at the end. So the RET teacher was able to kind of walk into a project that was almost ready-made, or I mean, it was readily designed, and it was really driven by the interest of the faculty member. This is one reason I suggest, talk to your faculty member if they've got interests in this kind of a paper in an education journal or journal of chemical education or something similar. The background is that silver nanoparticles are being used for their antimicrobial effects, and the question is, what happens when these antimicrobial silver nanoparticles get into the environment? So that was, in this case, we use an example organism, brine shrimp, which is, they tell me it's fairly easy to grow and not have them all die on you. I can't personally support or confirm that, but that was the target organism that they used. So the lesson overview was, it was targeted at high school, and traditional classes could have used this, especially in biology or chemistry or environmental science. So, and I think in field testing, the teachers found that students were engaged in this. They were motivated because they've heard of nanoparticles being used in sunscreen and household products like clothing. They've heard perhaps of silver nanoparticles being consumed directly, but that's a little bit different deal. So students were able to connect the notion that nanoparticles in consumer products can have a potential impact on the environment, and they were able to directly measure it. The activity was in pictorial form, sort of like this. The students did create the nanoparticle dispersions of both silver and gold, and these are fairly straightforward. This can be done in a high school laboratory, and perhaps you've already done it. They created a level of kind of a series of dilutions to determine the effect of concentration of both gold and silver nanoparticles on brine shrimp viability. So in this case, one had to grow a stock of brine shrimp, expose them to the nanoparticles, and then do some counting of who's dead and who's alive. And I mean, by dead and alive, I think it was mostly which ones are swimming and which ones weren't. And then by collecting data, you can really do a little bit more formal quantitative analysis of the effect of which type of composition of nanoparticle would affect the mortality, as well as the concentration of these different particles affect the mortality. So a very good project, resulted in a publication, which we'd love to see more of. A little bit different approach was taken by this teacher. This teacher was working with a group that was forming metal nanowires. So long aspect ratio, microns long, but nanometers thick nanowires. He was inspired to try to do the same thing, but what he did was he found an activity off an existing archive formed by the University of Wisconsin MERSEC group. And if you're not familiar with that as a resource, it's a wonderful place to find lessons of nanoscience and nanotechnology, especially great labs, great hands-on labs. The activity that he was building on looks like this. So if you've ever looked into the UW MERSEC materials, this is the format, and the procedure as developed by UW is use nickel, and used an electrochemical process and a template, which was a ceramic filter, to form these nanowires. So the teacher then riffed off that to use a little bit different chemistry, used copper, but the objective really was to introduce students to this electroplating process, A, which is very industrially important, and B, how to grow nanowires with it. In the process, was able to cover several topics in chemistry, like redox reactions, Ohm's law in terms of current flow, and then just a general introduction to the mechanism of metal electroplating. He also added, since he was a math teacher at heart, he added much more quantitative analysis in terms of yield, which is not present in the existing or the pre-existing activity. So this is a case where a previous activity similar to what you want to do is out there. You know, maybe you can think about how to augment it or how to bring it, bring some other aspects into it. This teacher in 2013 was working in a group that was interested in making sulfide-based semiconductors for use in photovoltaic cells, solar cells. Now, that was a little bit abstract, he found, for his students to directly carry to his classes. So he took a step back and looked at a more fundamental consideration of photovoltaics, and that is the measurement of efficiency. How much energy do you get out of a photovoltaic cell for unit energy of light in? So to do this, he was relying upon a number of commercially available, simple USB-based sensors for current and for voltage. Perhaps you've used these things. I think they're Vernier. They're called Vernier Go series. He also found a cheap source or a source of cheap solar cells, and then set it up so that the students would irradiate the solar cell with mostly incandescent bulbs, and took a very simple approach saying, what's the power input to that lamp? And what's the power output that we can measure, power being the product of current and voltage, to out of the solar cell. No allowance was made for the fact that incandescent bulbs themselves are very inefficient. So a lot of the energy goes off as heat. That would be the next iteration of this kind of process. Could you measure the heat evolved from an incandescent bulb? But at any rate, this was photovoltaic related, inspired by the RET's summer research project, but not at the level that he was working with in the lab. Another lesson that was inspired by the summer research was this by Dennis Ware. He was working with a group that was depositing magnetic materials for hard drives for very, very high density information storage. Now, the deposition process was highly technical and required a lot of the expensive tools that we have in our clean rooms. So Dennis took a step back and said, well, why don't we just get students to make a macro scale model of a hard drive? If you're a hardware nerd like me, you're fascinated by what's inside boxes. And here's what's inside a spinning disk hard drive, which, by the way, are getting more and rarer as we go to solid state memory storage. But hard drives are really a technological marvel. They are a spinning flat disk that's got a magnetic coating on it, spinning at high speed with a read head that's just kind of floating fractions of a micron above the thing. And the process is it's a big mystery for most people. So this teacher, who was a technical education teacher, he had access to a great shop. He said, well, let's build a macro scale analog of this sort of thing, the kind of thing that can be manipulated with human hands and played with, and see if we can replicate what happens in magnetic data storage. So he envisioned a system that would be based on like ceramic magnets, magnets which could be in one or two positions, north pole up or south pole up. And so putting that in a metal plate, that forms the platter of a spinning disk hard drive. Now we got to spin the thing. We'll spin the plate with a battery-driven motor, and then have some way to read that information. So the students would arrange the magnets in a certain way. This is where we got into the ASCII coding of ones and zeros, or strings of ones and zeros forming words in forming bytes. And by spinning this over some sort of readout circuit, one could simulate in macro scale what's going on in the micro and nano scale with a hard drive. So building this was a lot of fun. The metallic plate was just a pipe. It's a pan, a baking pan. It wasn't too hard to find the battery-powered drive or the ceramic magnets to be put on the pan. The trick was getting the readout circuit. You need a sensor that's going to be a magnetic sensor, and then some way to take the pulse from that sensor and turn it into a usable signal. So the sensors are commercially available. The circuit was custom designed by an associate, a friend of the teacher's, and then realized with an Arduino board. So this is, this is not for people who are completely new to this area, but if you're already playing in this field of working with Arduinos, for instance, or Raspberry Pi, single board computers, if you and your students are already can speak that language, this is a really fun way to emulate or simulate a nanoscale process that's kind of invisible and make it on the macro scale where you can really appreciate what's going on. So along the way, we could cover Faraday's law, the notion of magnetic flux changes, introduce the whole way that information is encoded using ASCII encoding. So strings of 8 or longer words of single bits, zeros and ones, can be formed into letters, numbers, and so forth. Students would attempt to code out their name with magnets on the metal pie plate and spin it around and try to pick up that signal and reproduce it. Bottom line is this was a really cool and fun way to do things, but it's tough unless you're already in this world of being able to fabricate fairly complicated things. And now that it's done, we do have the circuit established. We have something that can be reproduced elsewhere. And if it's something that you're interested in, maybe you could partner with the tech ed staff at your school if you've got a department like that, or maybe other institutions that maybe want to build up these things. I think there's a market for actually a commercial product that emulates these things in macro scale. Then we come to the group of lessons that really are not based at all on summer research, which is okay because many of these things were able to, many of these projects and many of these lessons, I think, are very successful in getting across nanoscale concepts. So in this case, let's see, this was Denise. She was working on a project that was constructing and testing a protein separator for a biomedical engineer. But her interests led her to say, could we explore, or could my students explore the properties of light and the interaction of light and matter and how that's used to study nanoparticles. So her lesson was based on exploring properties like refractive index and the light scattering of light by small particles. And the objective was to kind of build up that area of how optical properties can be used to analyze in these things like nanoparticles or even other materials as well. So her effort, let's see, I think we've covered the goals here. The topics covered were light interaction with matter, and then also applications of technologies to small particles, small nanoparticles. And the materials used were sand. And so sand was kind of qualitatively examined using light scattered in both wet and dry forms, and sand being wetted by water as well as organic solvents. And I don't think there's a quantitative component to this, but there certainly could be, maybe with some over-the-counter, off-the-shelf pieces of equipment. This is an assessment by the teacher after field testing in the classroom. Really felt that students gain a richer context of understanding of this kind of fundamental area of science. How does light interact with matter? Here's another case where the teacher was interested in getting across some concepts that are key to what we work with when we work with nanotechnology, but wasn't necessarily related to what he was doing in the summertime. His project was working on devices for biomedical imaging using light and ultrasound and so forth. During the process, he was making a thin film based device, and he used an ellipsometer to measure these films. And for those of you who saw the industry talk, it's probably a Woollum ellipsometer because they're the state of the art. This got the teachers thinking, how do you measure small things? You know, students are oftentimes, when they begin physical sciences, they have to measure something, or they're given the task to measure something, and kind of the notion of the importance of measurement is reinforced. In this case, the teacher wanted to try to get students to measure extremely small things that they wouldn't normally think they could measure directly. That, in this case, the wavelength of light, of a part of the white light spectrum. And also then incorporating uncertainties in their measurements, which is a key part of measurement science, and sometimes not appreciated by students who just say, what's the answer? What's the single answer, without a consideration of, well, plus or minus a certain uncertainty. So his process, well, here's a little background in ellipsometers, as you probably know. They bounce light off of usually some sort of transparent or translucent interface, so that the light is bouncing off the top and bottom interfaces of the layer, and there's an interference process that takes out certain wavelengths and reinforces others. So you can measure the thickness then of these materials. The lab itself was designed as a practical application of measurement. In other words, can you use this to measure something that we all see and experience, the wavelength of light? And then being able to carry out these measurement experiments and consider and evaluate uncertainties as part of the measurements and calculations. So not directly nano-related, but certainly supportive of a lot of STEM classes and a lot of, in this mathematics in particular. Here's a example of a lesson that was done by a teacher who was working in a material science lab and doing some depositing thin films of metals by molecular beam epitaxy, MBE, which is a high-tech procedure, not one that's easily reproduced in the classroom. But this is Mike's. Mike's a biology teacher. And so he said, well, can we make nanoparticles, and in this case, silver nanoparticles, by a biological process, and then something that's known generally as green chemistry, so that you use natural precursors to make silver nanoparticles, as opposed to some of the more chemical reagents used in the conventional process. And then once you've made them, can you explore their antimicrobial properties and compare them with commercial antibiotics? So in the activity, the students would learn about how they'd have to do some background reading on so-called biosynthesized silver nanoparticles, and then create these in the lab. And so making silver nanoparticles, perhaps you've done it. Typically you use silver nitrate as the source of the silver ion, and you reduce silver nitrate with sodium borohydride. Now, what is done here is, instead of using the borohydride, you use plant extracts, and you can use peppermint, aloe vera, geranium, a number of other species to get the reducing agent. So this was carried out. Students first had to make some antibiotic resistant E. coli. So this is a senior level class, and they had some experience working with bacterial conjugation kits and so forth. They were able then to produce antibiotic resistant E. coli as a target organism. Then they made the biosynthesized silver nanoparticles. And again, if you're familiar with this, it's a stirred wet chemical process, usually on ice. So, but instead of just reaching onto the reagent shelf and grabbing sodium borohydrate, they had to collect some plants, wash and grind them, and then boil the mixture to extract the active ingredient that's used in the reaction. So then following the procedure, they were able to create silver nanoparticles, a little bit different process than the typical reagent chemistry based one. But in the end, they got silver nanoparticles. I was able to confirm that doing some size distribution information analysis. So then they did the actual antibiotic efficacy testing with their target organism. And so comparing silver nanoparticles made by the biosynthesized route, as well as ampicillin and streptomycin, some commercial antibiotics. And then came up with, at the end had a petri dish, a culture dish that you could evaluate the efficacy of the antibiotic effect. In this case, they're measuring the zone of inhibition for the E. coli to grow in each disc. So a very interesting and sophisticated lab, but not related at all to the summer research project. Another one by the same teacher the prior year is particularly interesting. In fact, in the sense that it's very clever. It gets across actually a public health topic by using nanoparticles. In this case, again, he was working with thin beam or MBE films, and he's a biology teacher. So he said, what can I do with gold nanoparticles? And the fact that gold nanoparticles when they're dispersed in a liquid, you can cause them to crash out and turn color or get bigger by adding salt, sodium chloride. So the image on the left there is a focus, a close-up on a gold nanoparticle floating around in an ion or a polar liquid like water. There's a lot of ions surrounding the surface of that particle, and that's by design. Those ions will help disperse the particle, keep them from banging into their neighbors, because if they bang into too many and too often, they'll tend to stick, they'll get bigger, and then they'll start to settle out. You'll change the size of the particle, and it'll eventually get large enough so that it settles under gravity. With gold nanoparticles, the color that you get is closely related to particle diameter. So as the gold nanoparticles go from, say, 10 or 15 nanometers up to maybe 70 or 80, they've profoundly changed color. So you can almost see by eye the size change. And it turns out that ionic stabilization there can be disturbed by adding a source of ions like table salt. And so by adding salt, you will change the particle size, you will change the observable color. I took that into the realm of testing for how diseases spread. So first he had the class make gold nanoparticles in the conventional way, starting with gold chloride and then heating and adding some sodium citrate to reduce it. At that point, you've got small particles, 15, 16 nanometers or so. Then students would receive an eyedropper and a test tube filled with a little bit of distilled water, except one person was seated with a little bit, with a test tube filled with a salt solution. He then had the class interact with each other. And as he puts it here, he was having people kiss, but in the form of exchanging fluids, not bodily fluids, but the liquids in their test tube. And as a result, then there was some fraction of those test tubes that had salt water in them, some did not. So the question is, how do you detect that? Well, we're going to use our nanoparticles. We're going to use our gold nanoparticles by adding water from your test tube into the gold nanoparticle dispersion. You'll immediately find out if you had a salty solution or not. In other words, if you were infected with this simulated virus or germ. So this was a case where you could do some amateur epidemiology by trying to figure out where this came from. So a case of using nanoparticles and having students create nanoparticles, but putting them in the service of something in an entirely different field. So I found this one extremely clever. So that's pretty much it for the examples, and we can discuss how to do these things. I would encourage you to check out some of the lessons that have been produced overall by RETs across a number of sites within NNI and now NNCI. That's available on the NNCI website. I encourage you to check out NanoHub with its large archive of activities and publications and curricular materials. I neglected to put up the UW-Merced site, but that's also a great place to look for ideas and get an idea of what people have done in the past, how they've done it. And if you're interested in that photolithography setup that we produced here in Minnesota, please contact me. I'd be happy to send you all the instructions on how to get that started. That could be the basis of a project or a lesson rather that deals with fabrication of many different kinds of structures. So. Happy to take questions. It's early, I suppose, huh? It's early, I suppose. Can I ask the teachers, when
you,
I'm getting an echo, Quinn.
I'm getting an echo, Quinn.
Okay, so if I could ask the teachers, when you are tasked to add an activity, fill out a lesson, maybe interested in doing something new, where do you go for sources? Come on, teachers, unmute, give me an answer.
I normally just look for what's been done before and then try to make it my own.
Mm-hmm. So what's been done before? Do you have a favorite source for some of those things?
Just the internet. And on the internet.
Okay.
One of our teachers said, they go to RET quite a bit out of Colorado.
Okay. Has anybody used NanoHub? Well, then you have a great exploration ahead of you. It's a great resource. I'm reading the comments here. Okay.
Go ahead.
I do have a question.
Sure.
How fully formed does this lesson need to be at the end of our 6 weeks, besides, because we're trying to do research on something, we have to complete this, we have to present stuff. So how fully formed does it need to be? Just trying to avoid going back to grad school days of never sleeping.
Good point. I think in the past, we've been able to bring their lessons out to the point where they could be field tested after the end of the summer experience. So at some point in the academic year, we encourage students to trot it out with the full expectation that, it might not work optimally, needs a little tuning and so forth. But we would like it in the form where, you'd feel confident being up in front of your class and getting them set up with the simple equipment and walking them through at least a part of the activity. It's also suggesting, don't aim too high. We're looking for a nice clean single, not swinging for the fences. Any other questions, comments? Okay, well, I'll turn it back to Quinn.
Sorry, Jim, I was typing it because of the echo, which I don't know how to fix. We had to hop in this room really quickly. But one of the questions was, did the lessons include like an estimated budget for the teachers so they have a feel for how much these things would cost?
I see. I'm trying to remember the very comprehensive format we used under NNIN. There was a materials list and a source of, where you could find these things. I don't recall if we actually put cost estimates on there. Nancy, do you remember if that was a feature of the previous template? You're muted, Nancy.
Again, okay.
Okay.
So we didn't put cost estimates on them per se, but it depended on the lesson. If the lesson was using something that was a little expensive, we would alert by showing it. But if a lesson came in and said, go to the clean room and build this apparatus or thing,
Yes.
that lesson went to the reject pile. It was never published on NNIN or NNCI because it was not useful.
Right.
You can't do that. So if something's requiring like an expensive chemical that's in the couple $100 range, a good example of that is the quantum dot lesson on the website. Those used to be $100. for a set. Now they're 500 for a set. So that one we put in saying how much this is going to cost.
Okay.
We updated it for the current price instead of the old price, because that lesson was written probably 10 years ago.
Right. Again, it puts the onus on new teachers to kind of be cognizant of, is this doable? And part of that is can schools afford it? Can teachers afford it?
Right. So the old mantra was cheap, 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 easy, easy, easy.
Right.
But I'm going to do a pitch and say, really go and look at the lessons, or just look at the lesson list. I know there's over 100 of them out there, but it may give you some idea of what area of your biologist. You might just want to sort the NNCI list into high school biology, and then see what's out there that you could either build upon or come up with some ideas of interesting things to do.
Any other comments or any things in the chat box that I missed? I think most sites will work with you. Your site RET supervisor will work with you and kind of have a scheduled. Let's get the first draft by a certain date. Let's work on that. Let's get the second draft by another date. So to try to keep on, supporting your progress of producing these things throughout the summer. So it's not like we're going to ignore the whole thing and then boom, you got to have a beautiful finished product by the end of the summer.
That brought some relief to the teachers at Georgia Tech when you reminded them that, Jim.
Yes, this is a group effort, a joint effort.
All right, if there's no more comments about this, and I believe our next meeting is next Friday with you again, Jim, on July 2nd. My calendar is at the back of the room, so that's why I'm trying to remember if that is the next time we meet as a group. Oh, and we'll have the industry lunch, of course, next Wednesday, featuring industry speakers from Georgia Tech. And just to reiterate what both Jim and Nancy said, each site should be providing time for teachers to brainstorm and work together and work on their lessons and to.
So Quinn, is there no
And
meeting?
to definitely check resources. I don't believe there is one for all of us. Next Monday, Northwestern's teachers come on board. So they'll be catching up with everything that's been recorded. But the next time this group meets would be the industry lunch on Wednesday and then on Friday. But Monday is when Northwestern's teachers join us, I believe.
Great, and a reminder to the Minnesota. We're going to meet in person right after this.
Okay, and feel free to email Jim, Steve, myself, Nancy. Everybody should have everybody else's emails if they have questions about anything that's being discussed during these meetings, of course. And we do have time in the schedule later on in the summer. People will be presenting their research and their lessons to get feedback from their peers. So with that, I'm going to stop recording and end the joint meeting.
See you all later.